NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
In 1977, NASA launched Voyager 1, a car-sized spacecraft built to explore the outer planets and then keep going. For nearly 50 years, it's drifted more than 14 billion miles from Earth.
NASA says that Voyager 1 has become the first man-made object to reach interstellar space, the cold, dark region between stars, far from the influence of our sun,
sending faint signals home. But recently, those signals changed. Data began arriving in strange, precise patterns, too organized to dismiss as noise. At first, NASA thought it was a glitch. Now, they're not so sure. The inception. For over 200 days, NASA's spacecraft Voyager 1 was completely silent until it finally sent signals back to Earth, and we still don't know what to make of it. But first, we have to understand the peculiar journey of this space object so far. In 1977, NASA launched Voyager 1, one of two twin spacecraft designed to explore the outer planets and then journey onward into deep space. Its mission was ambitious: to visit Jupiter and Saturn, to study their moons, rings, magnetic fields, and atmospheres, and then press beyond into uncharted regions. Voyager 1 was sent just 16 days after its twin, Voyager 2, but on a faster, more direct trajectory, so that it would overtake its sister and reach Jupiter first. The idea was symbolic and hopeful. If an intelligent extraterrestrial civilization ever finds the spacecraft, they might get a glimpse of who we were. Although they share many mission goals, Voyager 1 and Voyager 2 followed different paths after the planetary flybys. Voyager 2 was directed on a grand tour path that allowed it to fly by Uranus and Neptune, whereas Voyager 1's path turned outward after Saturn and Titan, sending it out of the plane of the solar system. And as Voyager 1 raced outward, it made dramatic discoveries. Its flyby of Jupiter in 1979 revealed new moons, Thebe and Metis, faint rings, and charged particle effects around the planet. Then in 1980, it flew past Saturn, discovering 5 new moons and a previously unknown G-ring, along with complex ring structures and magnetic interactions tied to moons like Titan. The spacecraft's cameras and instruments also captured stunning images of the planets, their rings, and their satellites, giving humanity our first close looks at those distant worlds. After its planetary mission, Voyager 1 took what became known as the family portrait of the solar system in 1990. From a distance of about 40 astronomical units, that's about 40 times the Earth-to-Sun distance, it turned its camera back and snapped a now-famous image of Earth. A scientist named Carl Sagan later dubbed this the pale blue dot, a reminder of our fragile place in the vast cosmos. Now, beyond all the planets lies a boundary invisible to the eye but crucial in space science: the heliosphere. The heliosphere is like a bubble around our solar system, created by charged particles streaming from the sun, the solar wind. The outer edge of that bubble is called the heliopause, where the push of the solar wind balances the pressure of the interstellar medium. On August 25, 2012, Voyager 1 became the first man-made object to cross that boundary into interstellar space. Although the plasma science instrument that could have directly measured the change had failed in 1980, scientists used signals from the plasma wave subsystem to detect oscillations and density increases in the plasma around the craft. Once it was across that boundary, Voyager 1 entered a more stable magnetic environment. Inside the heliosphere, the magnetic field strength varied a lot under solar influence. After crossing, those fluctuations quieted, though the field strength itself remained in the same rough range. Scientists also noted that the local interstellar field direction measured by Voyager 1 didn't exactly match expectations, possibly because local distortions near the heliopause made things tricky. Even now, decades beyond the solar system's outer planets, Voyager 1 continues to send data back to Earth, though only a handful of its original instruments remain active and with power dwindling. The mission has turned off various instruments over time to conserve energy. The plasma wave subsystem, the magnetometer, and some particle detectors are among those that still work, allowing scientists to measure magnetic fields, charged particles, and the density and waves in the interstellar medium. And because Voyager 1 is powered by a radioisotope thermoelectric generator, its electrical output drops over time. So, as its power supply declines, ground teams must carefully decide which instruments to keep on and which to shut off. Engineers also manage the spacecraft's orientation, using thrusters to keep its antenna pointed toward Earth so data can still be sent across the vast distance. For decades, Voyager 1 kept sending steady data from the edge of the solar system, until something unexpected happened. The big disruption. In November 2023, something strange began happening with Voyager 1. Although the spacecraft still responded to commands sent from Earth and even transmitted a carrier signal, the actual telemetry data it sent back became unreadable. Mission controllers watched carefully. They knew Voyager 1 was still alive in some sense. It obeyed commands, aimed its antenna correctly, powered on where needed, but the information it was supposed to send was no longer intelligible. The stakes felt really high. Without readable data, scientists would lose the ability to monitor and understand what the spacecraft was doing, and in the worst case, could lose the mission entirely. As engineers dug deeper, they diagnosed the fault in the spacecraft's Flight Data Subsystem, or FDS. This is the onboard computer module responsible for gathering all of the engineering and science measurements, packaging them into a neat digital format, and passing them along to the telemetry modulation unit for radio transmission to Earth. Through a poke command sent in March, engineers requested a full memory readout from the FDS, and the results showed that about 3% of its memory had been corrupted. Further investigation pointed to a specific memory chip or bank that had failed, a stuck-bit scenario where part of the chip could no longer change state or reliably hold data. That failure made it impossible for the FDS to operate normally because the corrupted portion interfered with encoding the data properly. Engineers tried rebooting the subsystem, attempting resets and reboots, but the data output remained garbled. Because Voyager's computer systems are so small and old by modern standards, the entire memory of Voyager is under 70 kilobytes. They had very little wiggle room to maneuver. The mission team realized that the broken memory chip could not be repaired from Earth. No tool could reach out and solder or swap hardware across billions of miles. They needed a software workaround, relocate the essential code that had been stored in the corrupt bank into functioning parts of memory that remained usable. They identified unused or less critical areas of memory, broke the affected code into smaller parts, and reassembled them across multiple memory segments so that the FDS could still perform its role without relying on the damaged area. They also adjusted references in other code so that pointers and addresses would still link correctly. And so, on April 18th, they sent modified commands to Voyager with the new plan. Given the signal travel time, which is about 22 hours each way, they waited. Then, on April 20th, they finally received a response indicating that the workaround had succeeded. Voyager 1 began sending readable engineering data again. Despite this success, the spacecraft still faced limits. For a time, the science data channels remained offline, while engineers worked to re-enable full data flows. The fact remained that commands could reach Voyager. It could still hear Earth and respond, but for a while, no useful data could be read. During those dark months, the mission team knew this was one of the gravest moments in Voyager's long life. If the FDS failure had cascaded or cannot be worked around, they risk losing contact entirely. The ability to monitor spacecraft health, battery voltage, instrument temperature, and orientation depends on telemetry. Without that, the probe becomes a black box, just drifting silently in interstellar space. Fortunately, through tenacity and ingenuity, NASA was able to salvage the mission, at least partially, and restore the flow of useful data after months of silence. Voyager's restoration. After months of silence, Voyager 1, the farthest human-made object from Earth, began to whisper again. Once engineers at NASA's Jet Propulsion Laboratory managed to restore engineering data in early 2024, their next goal was to bring its scientific instruments back online. These instruments are basically the spacecraft's senses. They study magnetic fields, cosmic rays, and the faint plasma waves in interstellar space. Without them, Voyager 1 could still fly, but it would be deaf and blind to its surroundings. In May 2024, 2 of the 4 science instruments started returning usable data again, which was a huge milestone considering Voyager 1 had been out of contact for nearly a year. The team worked carefully to reprogram its 46-year-old computer systems, one command at a time, from more than 15 billion miles away. By June 2024, engineers were close to restoring all instruments that still had power, but Voyager's troubles weren't over. In 2025, engineers had to turn their attention to another challenge: its thrusters. These tiny rocket engines help the spacecraft stay correctly pointed toward Earth so it can keep its antenna aligned for communication. The primary set of thrusters had been in constant use for decades, and signs of wear were beginning to show. So, NASA made a daring decision to reactivate Voyager 1's backup thrusters, which hadn't been used since 2004. On March 20th, 2025, the mission team received confirmation that the heaters attached to these backup thrusters had successfully warmed up. It was a small but powerful signal that they were alive and ready to be used again. This success came just in time. NASA's Deep Space Station 43, the massive antenna in Canberra, Australia, that handles Voyager 1's communications, was scheduled for major upgrades between May 2025 and February 2026. That means there would be limited opportunities to send commands or receive data during that period. Getting the thrusters working again ensured that Voyager 1 could maintain its orientation and continue to communicate, even with fewer contact windows. The restoration of science data and the revival of its thrusters show that humanity's reach, though fragile, can endure against time and distance. And as one NASA engineer put it, Voyager may be old, but it's still talking, and as long as it talks, we'll listen. From what lies beyond the sun's reach to how interstellar space actually behaves, Voyager 1 has reshaped how we see our place in the universe. What Voyager 1 taught us. As the first human-made object to leave the heliosphere and enter the space between the stars, Voyager 1 has gone above and beyond in helping us see our planet in a whole new light. For scientists, it was like stepping out of a house and realizing that the air, temperature, and sounds are completely different outside. The instruments aboard Voyager 1 began to give us the first real direct look at what that environment is like. One of the most important things Voyager 1 taught us was about plasma, which is a soup of charged particles, electrons, and ions that fills almost all of space. Inside the heliosphere, this plasma is shaped and controlled by the solar wind, a constant stream of particles flowing outward from the sun. But beyond that boundary, in interstellar space, the plasma comes from other stars and the wider galaxy. When Voyager 1's instruments started picking up data, scientists noticed that the density of plasma outside the heliosphere was much higher, about 40 times denser than what it had been detecting inside. This confirmed that the spacecraft had truly entered a new region of space. Voyager 1 also helped us learn about magnetic fields beyond the sun's influence. Its magnetometer, a sensor that measures magnetic strength and direction, found that even though the magnetic field lines outside the heliosphere were aligned somewhat like those inside, they were more stable and less affected by solar activity. This means that interstellar space has its own structure and rules, quieter and steadier than the turbulent bubble of the solar wind. Another fascinating discovery came in the form of persistent plasma waves. Normally, plasma waves occur when charged particles move through space and interact with each other. Voyager 1 detected these waves in the interstellar medium, and they produced a faint but continuous hum that scientists were able to listen to, literally turning the data into sound. According to NASA's Jet Propulsion Laboratory, these plasma oscillations revealed that the region around Voyager 1 isn't completely silent. It's an ocean of gentle ripples caused by distant cosmic processes. Perhaps one of the most technical but meaningful findings was what scientists call the quasi-thermal noise plasma line. This means that as electrons move through space, they create tiny fluctuations in electric fields. Voyager's plasma instrument could pick up these small vibrations, forming what's called a noise line. The shape and frequency of this line reveal how many electrons are present and how energetic they are. By studying it, researchers learned that interstellar electrons behave differently than those within the solar wind. The quasi-thermal part refers to the slightly warm nature of this plasma. It's not as cold as deep space, but not as hot as the solar wind either. This discovery gave scientists a new way to map out electron populations beyond our sun's reach. However, exploring from nearly 15 billion miles away comes with serious challenges. The signals Voyager 1 sends are incredibly weak, roughly 20 billion times fainter than the light from a 100-watt bulb. It takes over hours and hours for a message from the spacecraft to reach Earth. Along the way, the signal is easily mixed with background noise, both from space and from the spacecraft's own aging electronics. Some of Voyager's instruments have also stopped working, and engineers at NASA have had to use creative problem-solving to keep others alive. And because the spacecraft was launched in 1977, many of its systems are far past their expected lifespans. The power source, a nuclear battery, produces less electricity every year. At some point in the 2030s, the energy will drop too low to run the instruments or the transmitter, and Voyager 1 will fall silent forever. Until then, every bit of data it sends is precious, because no other mission can currently replicate what it's doing. Even though computer models can simulate interstellar conditions, Voyager's in situ measurements, that is, direct readings taken from the environment itself, are unique. They give scientists real evidence to test and refine their theories. Without Voyager's direct data, we'd still be mostly guessing about what lies beyond the sun's influence. Of course, there are limits to what a single spacecraft can tell us. Voyager 1 is just one probe traveling in one direction, like dipping a single thermometer into the vast ocean and trying to understand all its currents. Scientists use its data carefully, combining it with observations from telescopes, cosmic ray detectors, and newer solar probes like Parker Solar Probe to build a fuller picture of the heliosphere's boundary. But Voyager 1 isn't alone out there. Its twin, Voyager 2, has been following its own path. And while they share the same origin, their journeys couldn't be more different. How different is Voyager 1 from Voyager 2? When NASA built the Voyager spacecraft, the plan was to send two nearly identical probes out into the outer solar system and beyond. But though they began as twins, Voyager 1 and Voyager 2 took different paths, made different encounters, and now occupy different places in space. First, the launch and path. Voyager 2 was launched on August 20, 1977, while Voyager 1 followed 16 days later on September 5, 1977. Although Voyager 1 launched later, it was sent along a faster, more direct trajectory so it could reach Jupiter and Saturn sooner. Because of that faster route, Voyager 1 overtook Voyager 2, reaching its first targets more quickly. Voyager 2's path was slower, but that also gave it more opportunity. After flying past Jupiter and Saturn, it went on to visit Uranus in 1986 and Neptune in 1989, making it the only spacecraft to have flown by those two outer ice giants. Voyager 1, on the other hand, had a trajectory that after Saturn's moon Titan slingshotted upward out of the plane of the solar system, so it could not continue outward along the plane to Uranus or Neptune. Voyager 1 sacrificed further planet visits in order to take a faster route and to get a close encounter with Titan. That divergence early in the mission is one of the main differences between them. Because of their paths, they also encountered planets differently. For instance, when flying past Saturn, Voyager 1 came within about 39,000 miles of the cloud tops, while Voyager 2's closest approach was nearer, about 25,000 miles. That difference matters for what kinds of data and images they could capture of Saturn's rings, atmosphere, and moons. Their instrumentation was mostly the same or very similar, designed to observe magnetic fields, particles, plasma, cosmic rays, and to take images. But over time, some instruments have failed or been turned off to save power, and the two are in different conditions now. Another major difference is their current directions. Voyager 1 is moving outward in a direction that takes it north, relative to the plane in which most planets orbit, while Voyager 2 is heading south. Because their directions differ, they cross the boundaries of the sun's influence, the heliosphere, and then interstellar space, at different times and at different spots, so they sample different local environments. In 2004, Voyager 1 crossed a boundary where the sun's solar wind slows down abruptly, called the Terminator shock, about 94 astronomical units from the sun. Voyager 2 crossed that same boundary in 2007 at about 84 astronomical units. Later, Voyager 1 entered interstellar space around 2012. Voyager 2 made that crossing in 2018. Because they entered different patches of that boundary, Voyager 2 measured a boundary that was thinner and smoother than what Voyager 1 saw, and a stronger magnetic field just outside that boundary. Voyager 2 also observed a clearer boundary layer inside the crossing, a change in density and temperature of the plasma, something Voyager 1 could not fully measure because its plasma instrument was not working. Their speeds differ too. Voyager 1 is moving somewhat faster, partly because of its slingshot path, and partly because of how Voyager 2's late encounters, especially at Neptune, modified its energy. In fact, during the Neptune flyby, Voyager 2's trajectory required a pass that reduced its heliocentric energy instead of boosting it, which partly accounts for why it's slower now. Over the decades, both have used fuel in form of hydrazine to maintain orientation and direction. Today, Voyager 1 weighs about 1,116 pounds, and Voyager 2 about 1,700 pounds, the small difference due to remaining fuel. Finally, in terms of instruments and operational constraints, both had many redundant systems, and many of their instruments have aged or been turned off to conserve power. And because Voyager 2 is younger in its mission progression and is in a somewhat different environment, the timing and sequence of instrument shutdowns differ between the two. Yet beyond all the science and engineering, both Voyagers carry something far more human, a message from Earth itself, meant for whoever might find it someday. The Golden Record. When Voyager 1 was launched in 1977, NASA gave it more than just scientific instruments. It also carried a message for anybody, anywhere, who might someday find it. That message is called the Golden Record. It's a kind of time capsule, a snapshot of Earth intended to communicate who we are to unknown beings in space. The Golden Record is a 12-inch gold-plated copper disc, much like an old vinyl record, but intended for interstellar travel. To protect it, there is a cover made of aluminum, and on that cover, there are diagrams and instructions. Those drawings try to teach how to play the record, how to interpret the images, and even how to figure out where Earth lies in relation to certain pulsars as a kind of cosmic address. On the cover, among other symbols, there is a depiction of the hydrogen atom in 2 states, because the time period between those states gives a natural unit of time anyone intelligent might understand. Inside, the Golden Record carries a mixture of sounds, music, spoken greetings, and images. The sound side includes natural Earth sounds, waves crashing, wind, thunder, birds singing, whales calling, and other animal noises. It also contains human sounds, footsteps, laughter, a baby crying, and even a mother's heartbeat. Then there is music. The record includes musical pieces from many cultures and epochs, classical works by Bach, Mozart, and Beethoven, traditional music from around the world, folk and indigenous songs, and even contemporary music of the time. On top of sound and music, there are also spoken greetings. 55 languages were used to say hello or a greeting from Earth to whomever might find it. There is also a printed message by U.S. President Jimmy Carter, who explained the mission and expressed hope that the record would convey goodwill from our world. Beyond sound, the Golden Record holds 115 images, including one for calibration, encoded in analog form. These images include diagrams of the solar system, mathematical maps, diagrams of anatomy and human reproduction, pictures of everyday life on Earth, people, buildings, landscapes, animals, and scientific diagrams, like the structure of DNA. The images are arranged so that someone knowing how to interpret the binary and pictorial clues on the cover could reconstruct them in order. One more personal and unusual inclusion is a recording of brainwaves. Anne Druyan, who helped put the record together, had her brainwaves recorded while she thought about Earth, life, love, and human history. That recording was compressed into a short audio form and included. Also, Morse code encodes the phrase per aspera ad astra, through hardships to the stars. The statement, to the makers of music, all worlds, all times, is hand-etched onto the record as a dedication. The idea behind the Golden Record is that perhaps sometime in the far future, some intelligent being or civilization might find a Voyager spacecraft, read the instructions, play the record, and receive that message from Earth. And who knows, they might find us before we find them. Voyager 1 is still out there, more than 15 billion miles away, moving deeper into the unknown every second. And somehow, through all that distance, it still manages to reach us. Whatever this new signal turns out to be, it's a reminder that even after nearly half a century, Voyager's story is still serving its purpose. If you want to follow what happens next and what NASA uncovers, like this video and subscribe to our channel because there's more coming.